This is the fourth part of lecture 4. This is a pretty long lecture. There are still another 70 slides to go. So hopefully I'll be able to finish it today and post it. Anyway, resin transfer molding, uh, we talked, we started talking about that. And basically it's a closed mold process where you are infusing a low viscosity polymer into a fiber preform, and you inject the liquid resin into the mold by a pump. And this is mostly used for thermoset type of resins because thermoplastic resins have pretty high viscosity. But there are times when you would use thermoplastic resins also by the same technique. And for resin transfer molding or for any kind of infiltration of a resin through a fibrous preform, the laws that govern that is called Darcy's law. It is mainly for composites, so you can define the time it takes for you for obtaining full infusion and what kind of viscosities are required and how much time is required. And because all these things are going to control the final properties of your composite. So in this case, this law can be used for both polymers, metals, and ceramic matrix composites. And in every case, the fibrous preform is a deformable or flexible porous medium. So it essentially describes the correlation between flow rate and pressure drop. So you know the maximum size of your part, maximum thickness of your part that you can make using this. And it, in chemical engineering terms, it describes the fluid flow through a porous medium. It is a general or a generic type of law, and it is an analog of the Ohm's law for electric conduction, or it can be also used to describe, similar laws are used to describe hydraulic permeability in the case of electrical conductivity. So essentially, you know the amount of permeability you need for this porous medium, and we are assuming a single phase fluid flow where you can know the volume density or volume per area time of the fluid. You know the viscosity, you know the pressure that you need to apply for infusing it completely, and you also understand the pressure gradient that will drive this fluid flow and fill this entire preform. So that's the law that is going to govern the processes like resin transfer molding. In the case of resin transfer molding, you are using a two-sided mold. It can be used for large complex shapes. It is relatively quick and you can have high fiber volume fractions. And just to reiterate, polymer matrix composites have typical volume fractions, fiber volume fractions of about 60 to 65%, and ceramic matrix composites have typical fiber volume fractions of about 40 to 45%. In the case of resin transfer molding, it is a closed mold process and there is very little emission of volatile organic compounds or VOCs coming through the process. Everything is completely closed and you can completely remove that. The next process that you have for composite fabrication is the automated process called automatic fiber placement. So you take a pre-preg, most of the time it is a pre-preg or a pretty sturdy fiber preform. You lay it down Most of the time it is just a um, fibrous pre-preg where the pre-preg already has got some amount of resin already infused into that, and you heat up this head and it lays it down, and then you compress it and make sure that it bonds well with the layer beneath that. So this is a process that is used very widely in automated processes for extremely large components, like for example the fuselage for the 787. And you can make it, you can have multiple heads, and you can have different kinds of toes delivered at different speeds, which allows for the building of a very complex structure. So if you have a curved surface, the outer toes of the bond will pull more strand length than the inner toes. So you can have individual toes and restart without stopping the motion of the head. So which means that your process can be automated and you can make very, very large structures. The compaction roller, it will consolidate the tape and it will press it onto the work surface. And you need a tool that is going to be holding it beneath, and it will, this pressing action will make sure that there are no gaps or porosity or trapped air between the individual toes. You can also have a fiber toe dragged through a matrix resin bath so that you can have very good wetting of the fiber and use that to lay it down and place it in the automated form. And you can have pretty large components, and this is one of the best methods for thermoplastic matrix composites. And what it can also do is you may press it down and then you can have a heating head going and consolidating the or curing the or partially curing the component before the whole component is placed inside an autoclave or something like that in order to cure the whole structure. You can also have a slight variation of the fiber placement called automated tape laying, and in this case it is a numerically controlled, CNC controlled pre-preg reinforcement tape, and it is also used for thermoset or thermoplastic matrices, and but in this case it is limited to flat or low curvature surfaces. So you can have pretty large components made by this technique also, and most of the time this is used for things like flight control surfaces and wing structures and things like that. So here is a automated tape placement type of equipment. You can actually go in and Google that and see the kinds of placement heads that you can get in the market. These are pretty expensive pieces of equipment, and it can have either 4 degrees of freedom or 5 degrees of freedom, and sometimes even 6 degrees of freedom to lay down the tape. Coming to autoclave based processes, the autoclave is a closed vessel, and this is used for making sure that there is pressure and hydrostatic pressure simultaneously applied over the entire component, and it gives you the best properties and the best mechanical properties. But of course, this autoclave means, I mean, the pressure used is only between 100 to 125 psi, but typical vessels can be as big as 20 feet in diameter by about 100 to 150 feet in length, which means that it applies considerable pressure over the entire component, and it's a expensive process. So here you have the autoclave for the Boeing 787 wing. So it has to be as long as the wing itself, or I mean, it has to be higher than that. And the door and everything can only be closed with with um, uh, gantry cranes, and it is again, the whole process is automated, and everything is extremely expensive, and it has to be completely controlled from start to finish. So what is the material that is used for many of these processes? Many of these processes are made with what are called prepregs. These are thin sheets consisting of single layer or multiple layers of fibers pre-impregnated with the resin, ready to be consolidated to produce the composite parts. So you only have one single layer of fiber tows, kind of either as a single toe, or you may also have multiple toes that are kind of woven into a single layer of the weave. You cut that and you place it into the mold, or place it in whatever shape and form that you want in order to make the final component. And then you have to laminate it in order to get the final shape. And this laminate can either be with or without what is called a sandwich material. So the sandwich material is usually used to make the final shape, and it is mainly used for reducing the porosity of the, or the reducing the weight of the component. So here in this case you have layers of carbon epoxy. You have fibers that are moving in this direction, and then you have fibers that are coming out of the screen, and here you have fibers that are moving in this direction. Or it can also be at an angle, so like plus minus 45 or plus minus 60 and things like that. And you can calculate the final properties of your composite using laminate theories. So here you have laminates of fibers coming out of the screen, and here you have fibers that are at an angle to this direction. And this is the prepreg. And that's what you use for making the final shape or component. You can also have chopped fibers, and you can blend it with the resin system, and you can inject that into a mold. So in this case, the fiber distribution is going to be totally anisotropic, and you really cannot say how much is the volume of the fibers in one single direction is going to be. You can also have a process called sheet molding. So you take a bunch of that sheet molding compound, and then you press that, and once you press it, because of the combined action of heat and pressure, this molding compound will flow and fill this mold completely and give you a uniform thickness. Coming to thermoplastic matrix composites itself, uh, why do people try to use thermoplastic composites? It's because it does not need refrigeration. If you have a thermoset type of a prepreg, the problem is that these prepregs have to be kept refrigerated. They can only be kept refrigerated for something like 1 year, I mean maximum 6 months. So beyond that, you really cannot guarantee the final properties of your component. The other thing is that with thermoset type of materials, you really cannot recycle this material. And they are also, because of the 6 month lifetime, they are also much more expensive than a standard type of a fiber matrix composite system. But there has been quite considerable amount of work that has taken place in the area of thermoset type of composites. So people are so familiar with the modeling and the use of these materials, so they keep using these materials again and again and again. Now, the other advantage with thermoplastics is that better recyclability. But they also have higher processing temperatures needed for making these composite materials. And they are pretty stiff and they lack the tackiness of partially cured epoxies. And the other disadvantage is that they are typically more expensive than thermoset type of materials. Discussing about laminates or prepregs itself, what do you do in order to make a composite? You have to stack the laminate of thermoplastics or thermoset type of materials containing fibers with very low resin content. Now here it says 15, but typically you can say that it is between 30 and 35%. That's very, very typical. Now, why do you need more than, this kind of numbers? I mean, why can't you have 95% fibers and 5% thermoplastic? The problem with that is that lesser the matrix, lesser will be the bonding between the matrix and the fibers and the bonding between multiple layers of the composite itself. So in all these cases, you have to consolidate them under heat and pressure. When you stack these materials, a good quality laminate or multiple layers of the laminate, a single layer is called a lamina, multiple layers is called laminae, Lamine, and the whole composite itself after consolidation is called a laminate of this composite material. We are still talking about thermoplastic composites, and in this case, when you are consolidating it, there must be sufficient flow of the matrix between the layers as well as between the individual toes. And you typically have a pressure of 6 to 12 megapascals, a temperature between 275 to 350 degrees centigrade. Now, remember that thermosets, the maximum processing temperature is typically 350 degrees Fahrenheit. And unless you are using things like polyamide or BMI and things like that, this processing temperature is not going to be higher than 350 degrees Fahrenheit. Okay, so thermoplastic composites are typical with matrices such as polyphenyl sulfone and polyaryl ether ketone. But the other advantage with thermoplastic composites is that you can make these composite parts within a very, very short time. So typical um, manufacturing times are less than 10 minutes each. So compare that with the regular thermoset type of matrices, which can take you almost an entire day to make. When you are making thermoplastics, you can also have uh, commingled fibers. So you can have continuous stores of carbon fiber and peak fibers to make drapable prepreg sheets. And you can have, so the advantage is that you can control the properties in different directions, and you can control the material or the fiber that is in different directions. So in this case, you can have uh, an automated tape placement of thermoplastic matrix composites. So you consolidate that and you locally melt it and you bond it between the top layer and the layer that is being laid down, and the bottom layer and the layer that is being laid down. So I'm not going to go too much into the detail of this, but essentially there is one technique that has been developed by University of Delaware. I would recommend that you go in and check out the technique that has been developed, that was developed by University of Delaware for making thermoplastic composites, and it is based on induction heating of these thermoplastic resin matrix composites. Okay. Now we can start talking about interfaces. That interface, even though it has one of the lowest percentages of a matrix system, of a composite system, it typically has an unusually high effect on the final composite properties. And what is the definition of an interface? It is the interface or the inter area between the matrix and the fiber. So there is a discontinuity between the two material systems, and that area is called the interface, and it may form in situ while you are making the composite, or you may want to add it as an extraneous process which will control the final composite properties. And it is going to control multiple properties of the composite. It can control, mainly it can control the elastic modulus, thermal expansion coefficient, strength, and fracture toughness. See, others are there, but the effect of the interface is not as strong as the case of elastic modulus, strength, and fracture toughness. So if you have a cylindrical fiber, I don't know why this went away, I'm not really sure. I apologize, but essentially what you have to understand is that if you have a very fine fiber diameter, it can lead to an extremely large interfacial area. And the interfacial area is controlled by the surface area of the fiber. Okay. I think we will talk more about it in some of the future slides, future lectures, but essentially I want to address every part of a composite system, which is what we are doing here. And the other thing I wanted to bring to your attention is um, a property called wettability. Wettability is the ability of the matrix resin to spread on a solid surface. So, that's with respect to that, we are going to talk about that. And it is controlled by how well that liquid can spread on that solid surface. So, when you put a liquid drop on a solid substrate, we replace that replace a portion of that interface by a liquid solid and a liquid vapor interface, because that's going to control the final properties of your composite and how well the matrix will wet the fibers. I'm not going to go too much into depth of here. I will let you read through this and ask me any questions if you have that. Okay. So you can have different kinds of properties. So what are the properties that are going to be controlled by the matrix system? So we will stop this set of this part of this lecture right here, and I will continue that in the next lecture, next part of the lecture.